Okay, so I assume everybody can see the screen. Hello, I'm Porcello from GSI Water Solutions. I think 3/4 of the people in the room and online know me for better or for worse. And hello to the rest of you. Nice to meet you. I have been involved for, gosh, a number of years. It's close to 30 because I know it based on when my first kid was born. Doing hydrologic studies and groundwater modeling activities over the years in the Spokane Valley Rathburn Prairie Aquifer System, working for the city of Spokane initially on its wellhead protection program, then the SAJB on its wellhead protection program, and later on some studies about the historical hydrology of the region and how groundwater and surface water interacts with each other. There was a lot of work that Ty Wick and I were brainstorming in the early to mid 2010s and did a lot of just terrific work there. So it's a pleasure to be back. I heard from various people that there was interest in updating wellhead protection areas and having some updates to the groundwater model itself, and that's what I want to talk about today. So I'm going to cover about 4 topics. First, just some objectives for what this work would be, why it would be done. Describe to you the study methods, which essentially constitute a scope of work we have in line for doing it. That relates to everything from setting up the groundwater flow model to conducting updates of the wellhead protection, delineated areas, doing some climate change analysis to look at how groundwater levels at production wells could change in the future. We're actually doing that kind of thing right now for the city of Spokane, and it's very eye-opening when you think about, what the implications are for, capital needs down the road. And I'll talk just a little bit about some documentation of that work. I've put together an estimate of what that work cost might entail, so I'll walk you through that. And then I'll end with a lot of visual stuff about the model that we've actually started to work on through the city, and that we can use as a jumping off point here. Good idea. Thank you. So so there's 2 objectives I've heard that the SAJB is interested in. The first one, of course, being to update the wellhead protection area capture zones. They're a little over 20 years old now, and there's actually been a lot of information we've learned about the aquifer system over the years since those were delineated. There's obviously been some changes to the well network for a few of the purveyors, so we would want to account for that in the model. But in the past couple of decades or so, we've had some improved understanding about the aquifer itself. Certain things we've learned about its lithology and some of its hydraulic properties, particularly in the eastern part of the city, where the city has been doing a lot of work, as you know, with putting in its Savannah well station, the new well station there, and some ongoing work at Well Electric that is supporting their capital planning. We learned some things about the aquifer we didn't know before. And to me as a hydrologist, these are like big incremental leaps in knowledge compared to what we had 25 years ago. And besides those specific locations, specific projects, there have been, since that time of these capture zone delineations, there have been aquifer and river studies conducted by the SAJB, the studies I mentioned a moment ago, the city of Spokane, and of course the USGS and Idaho DWR through the work they did to develop the bi-state model about 15 years ago. And then some work that Idaho DWR was doing at the same time as some of those studies, SAJB studies I mentioned, And we presented those at the River Forum conferences back around 2014, 2016. A lot of it having to do with questions about groundwater pumping impacts on Spokane River flows. So those have been some kind of milestone pieces of knowledge that we've gained over time. And then last but not least, a lot of what I do for a living is build and apply groundwater models. And I'll tell you, I'm glad the tools we have today are better than the tools that we had 25 years ago, because I wouldn't still be doing this. I'll talk a little bit about what that specifically means. I have some visual slides to show you on that. Besides the wellhead protection areas, I heard that there was some interest about using not just new groundwater information and the new groundwater model, but also climate projections that are out there to try to really understand what in longer term, periods of time, say 20 years, 50 years, 70 years out, what are the implications of both growth and climate change on groundwater levels, and what might that mean for pumping capacities in individual wells? And the reason this comes into play is that climate projections do show that there are going to be changes in the future. We think we've already seen some of them, as we saw in that study Ty and I were doing, and that was almost 10 years ago, hard to believe. But we were already seeing signals of things changing, and certainly up in the watershed surrounding the aquifer, what that meant for stream flows. And that in turn has some implications for natural recharge to the aquifer, just in terms of how this whole watershed aquifer system works. And the climate projections, and I've looked at this in a lot of detail in this area, partly for some of the work we're doing for the city of Spokane right now, but you can really see from those projections that they think that temperatures and length of the growing season could change kind of dramatically over the decades. And of course, that has potential implications for water demands. Obviously, conservation, can offset some of that, but we have to think about all these things together. And so why is that important? Well, this is one of the unique aquifers in the world where it's so crazy prolific that I had to unlearn half of what I'd learned in my hydrology teachings in college. And because it was so prolific, people haven't had to drill wells any deeper than necessary to get water supply, and they've not had to worry about tens or hundreds of feet of drawdown in water levels as they pump those wells over many years and many decades. And that's kind of unusual compared to a lot of other groundwater basins. So we've got, throughout the basin, we've got a lot of wells that basically skim off the top of what's actually a fairly thick aquifer system, because there's only so much operating head against which to work. The question is, well, if these natural water levels are going to start changing, what does that look like 5 decades down the road? And have we done capital planning to think about that ahead of time? Because the question is, are those changes going to be enough that it goes, that you look at individual wells and say, wow, okay, that might really change how we can operate these particular individual facilities in the future. And it's really in the summer months in particular that we're most concerned about that. So let me talk a little bit about kind of how we would approach doing these two activities. And they go a little bit hand in hand. They're not going to be two completely discrete, separate things, because they're both going to rely on using an updated groundwater flow model that actually the city of Spokane has already done a lot to, as you saw, the title of this agenda item was convert from MicroFEM to mod flow. Well, the city's done a lot of that already through some work that we're doing for them on various projects. And so we've been not only converting the software, but we've been using knowledge from these prior studies we've been doing over the last 20 years or so. We have new software that gives us all kinds of refined grading and layering capabilities we can work with. It uses what's called the mod flow family of groundwater models. That's the USGS groundwater model, and the early versions of mod flow that first came out in the 80s and were still around in the 90s and early 2000s were Yeah, sometimes they worked, sometimes they didn't. And starting around 2012, 2013, that landscape changed entirely. We have much more stable versions of ModFlow now, and versions that allow us to do a lot of really useful things with gridding techniques, so we can look at things regionally and very local scales at the same time, which is what the power of that MicroFEM model had been all those years. It was one of the few that was around in the 1990s that could actually do that. And we have all that now in the ModFlow family and much more. So developing an updated groundwater flow model is really, in a lot of ways, we've got a great platform for the SAJB to work off of. And what I would do is conduct some grid refinements around some of the SAJB member wells based on what we have already. And I'll show you some visual examples of that in a minute. The second step is that we would go and then start doing some forward-looking simulations where we put hydrologic inputs into the model. We would use published climate change factors relating to precipitation, stream flows, and all of that come out of a publicly available data source. It's called the Climate Toolbox. I think some of you are familiar with that because it was actually rolled out around the time that there was a kind of regional climate change effort going on here about 5-6 years ago that Oregon State University was sponsoring. And so what we would do, and we're doing this for the city right now, is we're actually looking at the latter part of the current century, looking at multiple greenhouse gas emissions scenarios, some that are optimistic, some are less so, and then have their own set of uncertainty bands around them that we kind of put all those in models, run them multiple times, simulate changes to the aquifer and to what the monthly water demands might look like as temperatures change in the region and customers have to like start watering, you know, their landscapes maybe a little earlier than is currently the case. So we would put all that into the model, you know, for both the SAJB members as well as what we've already done for the city. I'm envisioning that we would run the model 7 times. There's basically 6 climate change scenarios I have in mind, plus we've run the model for kind of the baseline current conditions we have right now, and then just start comparing all those runs to each other to see, okay, how much could water levels at each well change? You know, if it's this climate versus that climate versus a different climate. And this, what's great about this is the city's done all of work up front to define what a lot of those inputs are. You know, how much are we going to change stream flows under this climate scenario or that climate scenario? How much are we going to change the amount of flow coming in from tributary valleys that enter the basin? How much are we going to vary the water demands kind of on a percentage change basis? You know, how much does May look different than it used to, you know, for this scenario, that scenario, or another one? So we've got a nice platform to build on that we can then apply to each SAJB members' water demands and water uses. And I want to do all that because what I'd like to do is run those 7 models and then look at them and pick one that makes sense to do the wellhead protection delineations off of. And that would be a collaborative process with you folks. The main thing I want to point out about that is that the delineation approach and methods we'll use, they'll be the same as what was done 25 years ago in terms of deciding, you know, what the pumping scheme is. At that time, pumping rates were assigned in the model during delineation to be equal to the annual water rights volume. I think nobody would argue that that shouldn't still be the way to look at it. I mean, we can do something different if you want, but it seemed reasonable at the time. In those days, the special wellhead protection areas were delineated where we delineate them for a 1-year travel time in the aquifer multiplied by something called an importance factor. And that importance factor was related essentially to the response time to a contamination event, as defined up here on the slide. And the values of those response factors when I went back and looked at it for all the wells, it ranged anywhere between 0.1 to 5.0. And there was a whole bunch of things that went into each purveyor making their decisions about each well too. I don't think we used the same response factors for every well, if I remember right. And it was partly because there are different types of wells for different uses, you know. A purveyor may have 2 wells that are their primary source, and then a 3rd well is there for backup supply or, you know, emergency use if the peak day demands get unusually high, that kind of thing. We also thought about the availability of water from other purveyors via interties. And then there was a factor in there about, okay, you might say, gosh, wouldn't it be great if we could pump from this well more, but can the distribution system handle that amount? And so at that time, this is just a snapshot of a table that was buried in an appendix in that earlier wellhead protection report, kind of just to give you a sense of all the details and thinking and documenting, you know, how each purveyor selected the importance factor. And if I remember right, the higher the number, it was basically saying, if you went up, say, to like 5.0, you're essentially delineating a 5-year wellhead protection area. And that's because you're saying, we've got limitations in how fast we can respond to a contamination event. So if there's a contamination event at a well that's gonna take us a while to, you know, essentially deal with that contamination, we need to delineate as large an area as possible, which is why you might go up as high as the 5-year event. So you'll see the 5.0s, you know, like over here showing up in a, oops, whoa, what happened? In a place where, you know, we're saying, hey, the distribution system has limitations and what it can handle if we were trying to boost that pumping rate. And this is just a slide that has the footnotes that go along with that table. I won't dwell on this. I just wanted to give it to you so you have it to refer to later. And we'll come back and review all this stuff during the course of the project, but I wanted to give it to you now because it's obviously a really critical input and decision point. So we'll do that wellhead protection work. And then what I'm thinking is, I'll give you kind of documentation of the work in 2 ways. Obviously for the wellhead protection areas, there should be a written report, technical memorandum, because you need that for the state and for yourselves as well. I'm thinking on the climate change side of things, and this is just purely trying to save you guys some money. I'll give you a presentation on what that's finding. Let's not spend a bunch of time generating a report. And we've done it that way in the past with some of those studies we did with Ty a few years ago, and it seemed to work just fine. So trying to be a little helpful on that front.
It's a little helpful in the near term, but like try to go back and look at some of your stuff and go, oh, it's been a little problematic in not having a technical memo on those.
Or some kind of data like what you found from 1990, which is actually helpful to have, just some kind of documentation.
Yeah, okay, well.
I'm not the one paying the bills.
Yeah, and so part of me is like, yeah, let's, you know, do this as cost effective as possible, but at the same time, 5 years down the road, you're like, man, what was that? And trying to, you know, get some of the details.
Perhaps there's a hybrid also, you know, it's not a full-blown technical memo, but probably a paper. It could be.
Yeah,
or
a white paper.
Yeah.
Or even tables and like that you had for the other explanations, just that kind of thing that is document.
Yeah.
Being a computer type and model person, I know documentation is very helpful.
You're right. And then the other thing we could do, besides maybe kind of like a white paper memo that's short, is, you know, just make sure the PowerPoint presentation has, you know, a fairly detailed set of speaker notes in it. I've had that work at times before too. So anyway, happy to work with you on that. I just wanted to throw the idea out there, you know. We all need more reports to read, right?
I mean, there's value in having information in the future too, because who knows what we find in this, like, it's stark to the point where one or all of us need to go out for funding for improving our sources, replacing sources, finding new sources, like having some defensible data to back up a grant application of some sort, I think would be value add.
Yeah. Okay. All right, well, let's talk about the cost estimate in detail. So I'm thinking of this as essentially 4 tasks, a data gathering task, number 1, and then the actual model simulations, constructing them, running them, doing the QC on them. Then getting into the climate change modeling and the wellhead protection areas. Those would all be under a 2nd task, then a 3rd task to present the results. And then to do the documentation would be the 4th task. And again, we can make adjustments as however far you'd like all that to show up. With the concepts I had in mind, I was looking at a cost of about, I think it's gonna take about 75,000, and it's broken down. As you see here, I had heard ahead of the meeting, there was some interest, for example, about, well, what does it cost to do the wellhead protection areas versus the climate change pieces. And so, you'll see some of those here, but we're obviously doing activities that help both of them as well, like that 2nd line. So that's kind of how I see it breaking down. And I want to point out, I've gone back and looked, through our contract and our, work so far on the city of Spokane's full analysis of their wells, which we're getting near to completion on that. And, if they hadn't been doing all that work, the SAJB would be doing about $40,000 more to get it to this point. So I just wanted to let people know about that. Well, let me get you looking at some interesting visual stuff. I wanted to show you a few slides that relate to that groundwater model, what it looks like and what we've done to it to date in terms of its grid design and its calibration. So you might recall the bi-state model was a mod flow model. It had a grid that used regular square cells, much like you see here, but its cells were about 1/4 mile by 1/4 mile in size. What we've done in this newer software using the newer versions of ModFlow is built a grid throughout the SVRP where those cell sizes are 400 feet by 400 feet. And I call this a parent grid because it's just a starting point from which you can then do more grading work to look at things on very localized scales. And the other thing we've done with this model that wasn't in the bi-state model is, that aquifer is thick, it's several hundred feet thick. They had 1 layer in that model just about everywhere until you get up into Hilliard Trough, where they use 3 layers to represent what we know up there north of the city is kind of a upper gravel aquifer, then kind of a thick clay layer, 100 to 150 feet thick, if I remember right. And then there's another gravel package of the SVRP below that. So they use 3 layers up there, and these 1 layer everywhere else. So if you think about it, we've got an aquifer this thick. The wells are skimming right across the top of the water table. The river is above the water table, or if it dives into the water table, it's also just skimming the water table. So we've got these features that are, penetrating 1 to 10% maybe of the thickness of the aquifer. And so there's going to be a very 3-dimensional nature to groundwater flow patterns. And when you start thinking about where's groundwater coming from, how much might it be influenced by, say, the river here versus there, how much is it getting its water from near the water table where we may have a contaminant concern versus maybe it's pulling it from 600 feet down. You can't analyze any of that with 1 layer in your model. So we've got an 8-layer system in this model. And I set it up that way largely because in some of the work we were doing for the city and the SAJB about 10 years ago, we really needed to be able to say, okay, this well comes from the uppermost bottom layer, but this one over here comes from the second layer. They're not equivalent. And we want to understand those regional flow paths too. So we've got 8 layers, we've got this grid with 400-foot by 400-foot spacing, and then this is where the fun begins. We can start going and embedding local grids around areas of interest. And we can really do these anywhere we want, and we can turn them on and off and have multiple models that we've built off that original parent grid. So that original parent grid is always there as a starting point. But then we go, oh, okay, on this project, I wanted to go build fine grids around each of the city's water stations, well stations, excuse me. And I also want to have some greater resolution along the Spokane River, so we can look at those groundwater, surface water interactions in a little more detail than we need in the, outer areas, elsewhere in the aquifer. So in this case, I took that 400-foot by 400-foot cell spacing, made it 200 feet on a side along the river, and then went down to 50 feet around each of the city well stations. And when you zoom in, I'm going to zoom in next around well, electric, and park water, this is what you see. And, this is really useful because the dynamics of how water interacts between the river and a well, whether the well's really close to the river or farther away, you can really start looking at this with a little more confidence when you can do these things spatially. Now, what I didn't show you here is there's even other geometries we can use to these grids. I like these ones just because they're kind of visually easier to understand, but there are people who've built some really complicated grids using really complicated geometries to look at things. But this gives an idea, I hope, of what we can do. And what I like to do for the SAJB is build some of these fine grids around those members' wells. And so that way we can look at detail at, one of CID's wells, where you may have 3 wells at a certain well field, we can put each one discreetly in the model just like this. If you look carefully here, you'll actually see a well electric. There are a couple of different pumping centers in that location to represent, I think it's well 4 and well 5. And then lastly, I'll just wrap up, that's grid design. We also have to have models we feel are well calibrated, right? So we've been doing some work with this new version of the model to check its calibration. And there's 2 things we're looking at. One is how well do we represent the interactions between the groundwater and the Spokane River to the best we understand them. And so some people like to look at stuff like that in tables, and this is kind of helpful. I presented this to the city not too long ago, where at the time we had a version of the model, the one that we're working with now, we settled on in May of 2023, but I had presented at the last Spokane River Forum conference in April, kind of where we were at that time, and compared it to the bi-state model, and some losses it was estimating, and then what they measured in the field around that time, as well as what some earlier work in the 90s by Stan Miller had estimated. Well, these numbers are kind of all over the place. Here's a graphical way to look at it, which is the 1995 studies had a range of these numbers. Those are the 2 gray bars. The USGS work in the mid-2000s had a range. Those are blue bars. And the model we have now is the green. And it's been interesting to get the model to this point. Between Post Falls and Sullivan Road, what we're doing is we're plotting the gains and losses, not the absolute total river flows. It's the gain or the loss. So between Post Falls and Sullivan Road, we have a losing reach of the river, and these are the rates in CFS. This is actually in the low flow month of the year, so this would be August. And, the model right now is estimating around 300 CFS loss, and that tends to fit pretty well with most of the estimates. Interestingly, the field work the USGS had, it's something much higher. But none of the models really matched that in the past. At these other reaches though, Sullivan Road to Monroe Street, which is gaining, and then Monroe Street to 9 Mile Falls. It's been interesting that this model has wanted to estimate a little bit more discharge to the river than maybe some of the other models and the data sets have suggested. But for various reasons, it's hard to get that number down. And these readings are all uncertain to begin with. I cannot underscore the word estimate strong enough. So we're kind of in the ballpark. We also look at maps of groundwater elevation contours. The USGS had published this map back in their 2004 study of the water levels in September 2004, based on readings all across the aquifer. So these are contours of groundwater elevation. And, you know, basically over here near the state line, they were showing that the seasonal low groundwater levels were a little under 2,000 feet in elevation. When we were first pulling this model together, you know, basically what we're doing is we're like harvesting information from many different data sources, right? And then the model's telling us, okay, how well do all those different data sources fit together, and what parameters do you have to adjust to match the data sources? Which model parameters do you have to adjust? And so we were starting out here at the state line with water levels that were kind of high. They were about 20 feet too high over here. This was what I showed at the River Forum at that time. We got it down to something closer to that slightly under 2,000 number that we saw over here, and got to matching some of these contours somewhat better. I think there's still a little room for improvement, but overall I'm satisfied enough with it that I felt like, okay, now we can move forward with the work that the city had asked us to do earlier this year. So that's what I have. It's groundwater modeling. It's kind of boring. I hope I didn't put y'all to sleep too bad.
Except for those of us who are hydrogeologists.
Yeah.
That's fascinating.
Questions?
So one of the biggest interests will be going forward as people drill new wells or upgrades. How usable is the mod flow going forward? So
Add new wells.
to add new wells, you know, how much work would that be to, if they drill a new well, you know, how much? Oh yeah, we could do that for $80,000 to add another.
Yeah,
So
it's not that bad.
how easy is that gonna be for folks?
It's basically a straightforward process. The only thing that might introduce a little bit more than the usual amount of work is if we decide, well, it's kind of out in a new place and we'd like a fine grid over here. I'll have to go into one of the existing models and add that and all, but it's really not a big, it's not an $80,000 or $50,000 effort or anything like that, no. And that's what's nice about these platforms is they lend themselves very well compared to older versions of ModFlow to being changed, especially if you look at your grid and go, gosh, I really like more detail over here.
And then looking at your crystal ball in terms of the lifespan of this particular platform versus MicroFEM, which, you know, is this broadly used and a lot of supporters and all those good things?
Oh, yeah. So I built lots of MicroFEM models in the 1990s, and that was because ModFlow was not real stable. The visual tools were not very good, particularly in the early 90s. And here was this piece of software, MicroFEM, coming out of the Netherlands, I think it was, that could actually do those things, and they would crash too. Plus, it gave you these nice grids that allowed you to capture the regional and local scale effects, which you could not do at all with ModFlow in those days. And the landscape's totally flipped. Right now, there are two versions of ModFlow. That is what's basically everybody's using these days. Every place I've done a MicroFEM model has been now converted to a ModFlow model. And, you know, the USGS is all in on on mod flow. There were a couple of individuals, one who was inside the survey and one who was an academic who worked a lot with the survey, that did a lot of work in the early 2010s that improved the stability of the model in terms of just kind of the solver and the mathematics of the solver. But they also sort of reformulated all the ways that you take the groundwater flow equation, which is the math that governs this thing, and you turn it into a spatially distributed representation of a groundwater system. They kind of completely rethought the theory of that. And that's what allowed us to do these flexible grids now. That's what allowed us to use better solvers than we used to have before, and created way more. I used to get really nervous. I did have some mod flow projects in the 90s, and there would always be that moment where you go, okay, I built the model, I'm gonna run it for the first time. Is it gonna blow up on me or not? And you know, as a consultant, you've constructed a budget with the hope that it won't blow up on you, but sometimes it did, and that really sucked. And you know, if we were still in that world, like I said, I wouldn't be doing this anymore. So mod flows, these new versions of mod flows are here to stay. The USGS is continuing to do more and more with them. There's some folks in the private sector who do groundwater modeling as well, that have provided some input to the USGS over the years, telling them, hey, you need to concentrate on this or do this better. So it's in a very healthy place.
Tom, I have a question. So with your $75,000, does that include adding the new wells that we know have been drilled already?
Yes,
Okay.
absolutely.
So I know Rick's got one, and I believe Whitworth has one, and I don't know how many others there are, but we do have a number of new wells.
So this first line item is basically where I want to get all that information from you. I want to know how deep the wells are. I want to know, also work with y'all on what you want those importance factors to be, not just for the new wells, but also the wells we already have in here, that kind of thing.
Great, thank you.
Well, thanks, John.
Okay, look forward to helping you out.
Yeah, thanks for the model questions, Doug. That's a seriously important thing to gauge whether we're going into experimental land or something that is solid and.
Yeah, no, I don't want to see you guys going into experimental. I don't want to see anybody doing that. You know, maybe one other thing I can just tell you, if it gives you even a little more confidence, is in California, you know, they passed a law called the Sustainable Groundwater Management Act in 2014. And you have basins all over that state now that have had to develop groundwater sustainability plans under a very prescribed set of rules, lots of oversight, lots of public engagement. The State Department of Water Resources is reviewing a lot of those plans right now. And it's not just basins like in the Central Valley that were mining and over pumping their water. It was every basin that you know, whether it's urban or agricultural, that relies heavily on groundwater, had to develop these plans. So our firm has done probably about 8 or so of those. I've been involved very deeply in one of them, in a basin that was once agricultural, has become very heavily urbanized. It's north of Los Angeles. And the amount of oversight and attention that those things get is just gargantuan. And you know, they need groundwater models. Pretty much everybody that I know of is using the mod flow tool and using these kinds of tools I just showed you. So you'll be in good hands with these tools.
John, I have another question, again, about the financing. In the past, we've done some projects with you where we chunked it out over a couple of years. So does that seem doable to say, you know, have $40,000 in one year and $35,000 in another year or something like that, or as work is done, to not have to you know,
Yeah, well. Well, I'm thinking about how we want to set up. That they're setting up the simulations in the first place. You know, really, like, once we have those model runs. At that point, it's probably more efficient to just delineate everybody's wellhead protection areas all at once. It's gonna be actually less efficient to do some at one time and some at another.
I was thinking back to your chart we had, you know, some of the tasks before you got to climate change. I mean, so I'm just wondering how it could be, if it could be broken up at all, just thinking about our finances.
You know, probably the easiest way to break it up would just be to say, what if you were gonna do the climate change simulations later? And make an assumption about what you wanna look at for the purpose of doing your wellhead protection areas. Maybe you do those just based on, you know, essentially current conditions with little or no climate change baked into it. That'd probably be the more straightforward way to do this.
But not as desirable.
I don't think so, because if I'm a water utility, you know, the city of Spokane is feeling this already. They've got one of their well stations right now where we think the amount of climate change there is notable enough that it's getting them to pay a little more attention to what those capital improvements might need to be. And we're not talking tens and tens of feet of climate change, but it's less than that. But because of how little they penetrate the aquifer, it actually means a lot more. If these wells all penetrated 100 feet below the water table, I wouldn't be as worried about it, but most of them don't.
Okay. Thanks, John. Any more questions?
Just throw out one comment though, you know, when we talk about the model, the city of Spokane, where they're at in their development, and I think, you know, SAJB, and then we look at IWAC on a regional acceptable model. I think that there's some importance and consistency throughout that, you know, to be a real regional model, a true by state model. In replacement or upgrade from the 2007 USGS. So I think that's an aspect that should be considered as well.
Okay.